We'll continue here with the second module that's in Chapter 26 on direct electric currents. And we'll continue with that module by discussing the RCV circuit. The RCV circuit is what it implies. It's a resistor, a capacitor, and a voltage. And if we draw this, we can take our voltage like this. This is the symbol for a battery. A battery might have any voltage. We could pick 12 volts for this one. This is the positive end of the battery, and the small minus sign is always the negative end of the battery. And in this circuit, we're going to have a resistor. This is the symbol, a zigzag line like this is the resistor. This is the voltage. And this resistor, of course, is symbolic for the fact that when current flows through a system, it's going to lose energy to heat, and that's what happens in a resistor. So it's a loss of energy to heat as the electrons try to go through the system. Then we have a capacitor, and we're going to connect this around and put a little switch right here so we can throw this switch and turn this circuit on. Until the switch is thrown, there's no connection. So this would be the capacitor. Now we might give this a capacitor capacitance of something like 4 and a resistance of 2. This would be 2 ohms and 4 farads, just for the purposes of calculation. Now how do we deal with the circuit? How do we predict what's going to happen? Well, when we throw this switch, then these electrons here try to get away from this end, and they're repelled around here, and they're going to move around and they're going to accumulate on this capacitor. That's going to push electrons away from this end, and these electrons here are going to run around here through the resistor and accumulate because they are attracted to this positive end of the battery. That will leave this end negatively charged and this end positively charged. And if we think about what's going to happen, that's going to surge at first as the current races around, but as the current does that, more and more negative charge accumulates here. It's going to slow down the flow of this charge until finally it essentially stops. It will stop when the voltage across this capacitor is equal to the voltage across this battery. Now we need to know, in order to work this problem, how resistance is related to voltage. And you remember that we had the equation voltage is equal to the current times the resistor, or resistor times current. And for a capacitor, you recall that the voltage was equal to the charge divided by the capacitance. Now, as I think about this and add these up going around this circle, I basically have the fact that this plus this, where these two are negative, is going to be 0. Well, I can take these two voltages and move them to the other side, and I would end up with R times I plus Q over C is equal to the voltage V. You'd say, well, how do I solve this? Well, this is a rather complicated equation. Although the voltage is constant, the capacitance and the resistor, the charge that's on the capacitor is actually a function of time, and it's changing. And so is that for the current that's flowing in the system. So in fact, I probably should move this down so the reader can kind of see what's happening here. These are the equations that I have written right here. And you'll notice that in this right here, the current I is equal to the change in charge over the change in time. That's actually a derivative, because the current is the flow of charge per unit time that goes past a given point. So I can rewrite this equation as R dq dt plus 1 over C times Q is equal to V. This is a first order linear inhomogeneous differential equation. First order, because the first derivative is the highest. Linear. It's linear because the derivative and the function Both have a constant multiplying it, and there are no powers or square roots or logs or any other functions, just constant times the first derivative, constant times the second derivative. And it's inhomogeneous because there's a constant term left over on the right-hand side of the equation. So that's how we describe that equation. You can say, well, I'm not sure how I can go about solving that. Well, it's not really hard, because I'm going to tell you what the solution is. To all of these linear differential equations like this, the solution is Q is equal to A e to the alpha t plus a constant B. That's a constant, alpha is a constant, and so all the solutions depend upon time in an exponential way. But I have to see what works here. So in order to do that, I plug this in and see what constraints this gives me. Now watch this. When I take the derivative of this, the derivative of b is 0 because it's a constant. The derivative of this, therefore, is alpha, and alpha comes down every time I differentiate an exponential. So this is a alpha e to the alpha t. So I'll get r, first derivative of this is a alpha e to the alpha t. Then I have plus 1 over c times the q again. So it's plus 1 over c a e to the alpha t plus 1 over c times b, and all of that is going to be equal to the voltage. Now you'll notice here that there are two types of terms. One depends upon time. We're going to take those two together and we're going to factor out e to the alpha t and the a. That will be r alpha plus 1 over c a e to the alpha t. I've just factored out this term. I'm going to bring this term to the far side of the equation where it becomes v minus b over c. Now you'll notice something quite amazing. On this side of the equation, I have something that depends upon time. Over on this side, I have a constant. That's not possible. It's not possible unless both sides of the equation are equal to 0. How can they both be 0? They can be 0 only if this term is equal to 0 and this term in front of the exponential is equal to 0. Doesn't matter what a is equal to. So first of all, let's look over here, and this puts a constraint on b because we have v is equal to b over c, and in order for these to be the sum to be 0, or I can solve for b and we can see that b must, put a little must up there, b must be equal to v times c. That's our first result. So we've determined what that b has to be. Next we can look at this term over here, and this term doesn't make a restriction on alpha. Alpha can be anything, but it does constrain, a can be anything, but it does constrain alpha, and we get the equation r times alpha plus 1 over c is equal to 0, and that's solved easily in your head. Alpha is going to be equal to minus 1 over rc. And that's our second constraint. So now we can say this is a solution. Is a solution. If and only if this equation is true and this equation is true. So we can substitute these terms back in here, into here, and what we get is q as a function of time is equal to a constant which can be anything, e to the minus t over rc plus vc. And this is the solution to the equation. And you can see that what happens is over time, if we take the capacitor and there's no current flowing in the beginning, then that could be a condition. We can take the derivative of this and say, what would that mean? And let's look a little further down on our page here to see how that's managed. We see here that we did conclude, right here on our notes, that alpha is minus 1 over rc and b is q at time equal to 0. That's V times C, and you'll notice that V times C is the charge that's initially on the capacitor. Well, that charge usually is 0 initially, and so we could make that V is equal to 0 initially, and then or we could decide what it is, depending upon what are called the initial conditions. The term RC is often called tau, or the time constant of the circuit. It depends upon the product of R and C, how fast this circuit is going to go to the final state. And one thing is kind of like half-life. We can say it's in a time of RC, it's going to go to 1 over E of its value. You can see that happens when T is equal to R times C. This becomes E to the minus 1, or 1 over E, and you call E is 2.71828. So that's about 1/3. So it goes to 1/3 of its final value in a time T is equal to RC. So we define that as tau. It's called the time constant of the circuit. Now we notice that RC has the units of time, and that has to be because all transcendental functions have to have a dimensionless argument. Okay. Let me move this up just a little bit. We can see what's happening next. If our charging voltage is applied at time t is equal to 0, then we can rewrite this where if we think about our constant B as being V times C, which is the initial constant, it would be Q, and so we could write this as in the form that we have right here, that Q of t is going to be equal to Q naught, the initial charge, times 1 minus e to the minus t over RC. Now that arises because you can see that if at t is equal to 0, e to the minus 0, or e to the 0, is going to be 1, and this says our charge originally is equal to 0, so it satisfies those conditions. So when t is equal to 0, this term here becomes 1. We have 1 minus 1, which is 0, which says originally we have no charge on the capacitor. Later on, toward t is equal to infinity, this term here becomes e to the minus infinity, which is 1 over e to the infinity over RC. Well, this becomes 0, and in that particular case, you see at an infinite time in the future, this approaches 0, where originally it approached 1, now approaches 0, so we have that the charge finally, at an infinite time in the future, the charge at infinite time is going to be equal to just Q naught. And so it charges to a full charge of Q naught, which is what we originally said back here. We said that B must equal to V times C, where this is V times C, which is the charge that's on the capacitor. If we're discharging the capacitor, then we start out with a charge, and we find that the charge dissipates, and the equation doesn't have the constant. It's just Q naught e to the minus t over RC. Why is that? Because if I look at e to the minus t at time t is equal to 0, this is saying that Q is equal to Q naught originally. But eventually, this becomes 0, so finally the charge is all dissipated from the capacitor. That would be the case where there's no voltage here, and we just connected the system straight across here, what used a charged capacitor. That would be the case of where this equation is what we call homogeneous, so that the voltage over here is 0, and we only have these two elements. Of course, if the capacitor were not charged in that case, nothing would happen. So the capacitor has to be charged if we're going to just connect straight across here and ignore the voltage. And then that equation discharges our capacitor. The current in both cases can be obtained by differentiating the charge as it flows in the system.